All right, we're back. It's a new day in my world. It should probably be the same day in yours, but it doesn't really matter because right now we're faced with a question based on the data we got from the previous part of this video or the first part of this lecture. And we're looking at VOT scores VOT measures from the people that took this class 10 years ago. We hypothesized that we had a mean VOT of 100 milliseconds for aspirated stops, and we found out for this particular group, we actually found a sample mean of 94 milliseconds of VOT for the aspirated stops that they produced. And when we did the math, or the stats, I guess you could say, we calculated a z-score of about -3 for that sample mean based on this hypothesized sampling distribution. And if you convert that to a probability for a normal distribution, you find that about 0.2% of the distribution is to the left of that value. And so that's what we're going to use. That's the sort of piece of evidence that we're going to use to try to jump to a conclusion about what's going on here underlyingly in our data. We need to make a decision about whether we should accept or reject that hypothesized mean. And I asked you to kind of come up with an instinctual answer to this. Maybe you already did that well before I asked the question, but today or in this particular part of the lecture, I want to walk you through how to do that sort of formally. Okay, so it might help us to walk through the principles or some basic terminology behind the principles of interpreting the results of these hypothesis tests before we get to sort of what the actual answer is. And so I'm going to give you two to begin with. One is that our null hypothesis is that VOT equals 100 milliseconds in this particular case. So it's kind of a funny term because it's just what we start off with, null hypothesis. I guess if you think you start out at 0, you can think of this as like your basic default hypothesis, and it's represented as H sub 0, maybe for that reason. But you can contrast that with the alternative hypothesis, which is represented with an H sub A. And in this particular case, we were testing that hypothesis, which is that VOT is less than 100 milliseconds. That was a particular stipulation of the test we used, that we were looking at the less option, not the greater than or the both sides options, which we will find out eventually are valid options as well. For now, we're just looking at the less than option, and that counts as what's called our alternative hypothesis. In some cases, I will ask you to sort of make explicit what your null hypothesis is if you're sort of going through the hypothesis testing regime for some set of data in this class. And I've had students who found that, number one, it's useful to make that explicit, I think, so you can like clarify what you kind of imagine the data to be structured like, I guess. But most people don't do that when they actually write up, say, there were statistical results for an academic or journal article. It's okay if you keep doing that, but just know that it's not sort of the conventional way to do it. In this case, I'm going to make these explicit just to make sure that you understand exactly what we're doing here. So we've got a null hypothesis, that's what we started off with, and then we're going to either accept or reject that. And if we reject that, then we're going to wind up with an acceptance of our alternative hypothesis. So we're just choosing between one or the other, basically. As I said before, the null hypothesis is our default assumption, basically that nothing of interest is going on in our data. If it helps you to think of null as kind of being equivalent to like nothing, that might be an easy way to remember how to describe it. Because it's the default, it's the idea that nothing exciting is going on, and the alternative hypothesis is that something exciting is going on, and that exciting thing is basically that the null hypothesis is wrong. And I want to give you, or go back to another example of how to think about this. If you remember, I showed you that video of the face in the clouds in New Brunswick back a couple of lectures ago. I'll show it to you to jog your memory in case you've forgotten. But remember, there's this dude out filming the clouds in a thunderstorm behind his house in New Brunswick for whatever reason, and then this face emerges eventually. And we know, as scientists, as people of reason, that there's lots of turbulence in these clouds, and they make all sorts of funny shapes. We know you can always look at a cloud, or often look at a cloud and pick some sort of shape out of it. That just happens naturally, right? There's a lot of randomness in there, and sometimes that randomness can look like a pattern that we recognize. it doesn't mean that the clouds are trying to make a face or that this is somehow representative of an actual face. We get this randomness in this pattern in this particular case, this face, as a result of just these natural forces. So our null hypothesis, or another way to look at that is I'm asserting in this particular case that this face is the result of just these natural forces. That's the null hypothesis, that sometimes this face will emerge. The alternative hypothesis would be that it's not just happenstance, that maybe God is putting a face out there to give you a warning to don't film clouds in your backyard in New Brunswick or something like that. Otherwise, things get gnarly. Who knows, right? So, but the null hypothesis should be basically the simplest explanation of the phenomenon at hand. And we're testing how likely it is to get a pattern like this given that null hypothesis. And, I don't know how often you see faces in the clouds, maybe every now and then. Like I said, when I first presented this, we're kind of tuned in to recognizing faces out in the world because they're important to us as human beings. So you might see it more often than a dog would or what have you, but it doesn't happen all that often. The question is how often actually counts in this sort of paradigm of hypothesis testing. So in hypothesis testing, we have this null hypothesis that nothing of interest is going on. It's all just random forces in the universe. And we collect some data related to that hypothesis. We then make a decision based on that data about whether or not we believe the null hypothesis is true. An important point before I tell you how to make that decision is that we do not actually find out whether or not that null hypothesis is true. We just make an educated guess or an interpretation of the data. This is one of those sort of frustrating things about stats is that it's a little loosey-goosey. At the end of the day, we're always kind of just making guesses, and we're not really totally pinning down exactly what's going on in most cases, especially not with this paradigm, right? It doesn't afford us that opportunity. It just tells us how to make the best or educated guess we can. So in order to know how best to interpret the data, it's still useful to conceive of an objective truth of the situation and then how our interpretive decision relates to that truth. So as, imperfect human beings, as imperfect scientists, we're not ever going to know for sure what the truth is. But if you want to think of God or a higher intelligence or an objective reality out there, do so for the moment because it's going to help us figure out how to relate that objective truth to what we can actually observe. And there's going to be a slight mismatch between the two. Okay, so let's say in the objective world, our null hypothesis is actually true, like the VOT of those aspirated stops produced by those speakers, the mean VOT of that group of stops is actually 100 milliseconds. Yeah, call it what you will, whatever your null hypothesis is. If you accept that null hypothesis when it's actually true, the term for that is either a hit or a correct acceptance is what I'm calling it here. And when you accept that null hypothesis, you reject the alternative hypothesis. So the the mean VOT of those aspirated stops can't at the same time be both 100 milliseconds and then also less than 100 milliseconds. You're picking one or the other, right? That's what we're doing with this little game. I've got some notations over here on the right, which involve some Greek letter variables. I'm not going to explain what those are at the moment, but I will explain those in the next couple of slides. And this is just kind of help you relate the terms here to these values over here on the right, which we'll see again. If that null hypothesis is true, if we're positing that nothing exciting is going on, and then we reject it, and we say, we think something is going on, that's our best guess, then that's called a type 1 error. So we're accepting the alternative hypothesis even though the null hypothesis is objectively true. It's called a type 1 error in some circles. Another way to think of it is a false alarm or maybe a false positive. I've heard that term as well. And that relates to the Greek letter alpha. But basically, this is the situation where you think what's really going on is nothing, like it's just turbulence in the clouds. And then you reject that null hypothesis. You think, no. God put a face in the clouds for a reason. Not to belittle anybody's religious beliefs or whatever. I just don't think clouds are all that important as far as that's concerned. But that's the idea, is that you think this is sort of like something's going on here. This face in the clouds means something. It's not just randomness, right? Okay, so if the null hypothesis, on the other hand, is false, then if you accept the null hypothesis, even when it's objectively false, that's a different kind of error. So this is called a type 2 error or a miss. So in this particular case, something underlyingly is actually going on because the null hypothesis is false, but we think that nothing is going on. And so that's just a miss. We're missing a pattern when we should be seeing it. And that relates to this Greek variable beta. And again, not to ruffle too many feathers here, but this I've noticed kind of tends to be the case with political correctness, where people will sort of just kind of dismiss a general pattern between, say, groups of people if there's like one counterexample, because they don't want to like emphasize differences between groups of people, say. That's the politically correct thing to do. Yeah, so the issue there is that these patterns we see in the natural world are often variable. They're not absolutely perfect. So you have to kind of make a decision about how much evidence you need to say, well, there's differences going on between these two groups of things. Or maybe there's not enough of a difference going on such that they're basically the same underlyingly. Yeah, don't want to dive into that too far because, like I said, I'm not trying to ruffle too many feathers, but I think that's a common example that you find out in the world these days of that sort of error, the type 2 error or a miss. If the null hypothesis is false and you reject it, which is basically what you should do, that's called a correct rejection, and that relates to this quantity 1 minus beta. So in this case, if the null hypothesis is false, something is going on, and then you say as a result of your experiment that, oh, something is going on. So, if somebody, I guess, to give you a different example from the face in the clouds, if like somebody like goes on a wall and like paints a face there, and you come and say, oh, this isn't natural, somebody must have come here and drawn a face of some sort. It didn't just happen because of the rain splotches or something through a thunderstorm. Okay, that's a correct rejection of the null hypothesis, which is that it's all randomness, right? Okay, hopefully this makes sense, even though I've been kind of talking about it in a random, turbulent way. If it didn't, I'll give you multiple other chances to try to make it make sense. So I normally draw this stuff up on the board, which is why I'm trying to walk through it kind of painstakingly step by step, because it helps to take a lot of time with this. But this is at the core of what we're doing, our decision-making process when we go through the null hypothesis significance testing paradigm. Look at it a different way, kind of organize the variables in a different orientation. We've got a reality here. Here's our objective reality. Either the null hypothesis is true, nothing's going on, or either the null hypothesis is false, something's going on. If you look at the decision sort of dimension of this process, if we accept the null hypothesis and it's true, that's called a hit. If we accept the null hypothesis and it's false, that's a miss. So again, this is something's going on, and we miss it because we think nothing's going on. And then in the other decision, half of the decision world, we reject that null hypothesis. We think something's going on. And if it isn't going on, then it's called a correct rejection. If we reject the null hypothesis and something is going on, i.e. the null hypothesis is false, that's a correct rejection. Yay, we identified that something's going on. And if there is nothing going on and we still think something's going on, that's called a false alarm, right? Which hopefully is fairly intuitive. If your fire alarm goes off at your house and there's no fire, that's a false alarm, right? Another way to think about this, stepping aside from religion and politics and getting into a different controversial topic, you can think about this in terms of COVID testing, if you will, right? So the reality might be if you go get tested for COVID, your null hypothesis, let's say, is that you don't have the disease. And your alternative hypothesis is that you do have the disease. And what you're kind of trying to find out, generally speaking, is whether or not you do have the disease through the test. But there's two different kinds of mistakes that can happen. So in this case, you don't have the disease, but the test tells you in the false alarm case that you do, right? So that's a false alarm. Or a false positive is how people have been referring to it in the media recently. And the alternative to that is the false negative case, right? So in this case, you actually do have the disease, but your test says, no, you don't. So that's a miss, right? You're missing the fact that you do have this disease. That's a false negative. False positive, false negative. False positive is false alarm. False negative is a miss. And I gave you different terms for these errors. I said that a false alarm is a type 1 error and a miss is a type 2 error. And you will hear people use that terminology from time to time. I remember giving a job talk many years ago where somebody just started talking about type 1 errors, I think. And then I had to like jog my memory, like, what the heck is a type 1 error? And I'm going to give you kind of a mnemonic to remember that. A false alarm, the false positive, is the type 1 error. We think that something is going on even when it's not. And the reason why that's type 1 is because we tend to make that error more often as human beings. So as human beings, we are sort of generalization machines. We're really good at finding patterns out in the world. When we look at the clouds, we often see faces or the shapes of animals or whatever, even though there's not really any reason to think that those patterns were put there in any intentional way or that they actually represent like a bird or a human face or whatever, right? We tend to see patterns. We make that mistake a lot more often than the other type of mistake. And because we make that mistake more often, it's the type 1 error. It's the primary kind of error we make in this decision making process. So a miss is a type 2 error. False alarm is the false positive. A miss is the false negative. And the miss is where we think that nothing is going on even when it is. So in that particular case, I guess you could think about this from an evolutionary perspective, perhaps. Like, if something out there is trying to kill you, you don't want to miss that, right? So it can be more expensive perhaps to miss patterns out in the environmental world that are happening around you. So we're more finely tuned to think that something is going on. There are dangers that don't really exist. But these misses still happen. These false negatives will still happen, but they're known as type 2 errors because they're just less common. So the question I want to pose to you now, or at least have you think about, is how often are we going to make these mistakes as statisticians? And it turns out that we can actually decide how often we want to make each type of mistake. So we can determine how often we're willing to be wrong. And I'm going to lay out this table or tabular format for our terms again, and then kind of relate them to these variables that I mentioned before, alpha and beta, to represent how often we make each kind of error. This is also kind of technical, and I want to walk through it relatively slowly. So these are just the terms to remind you of what I mentioned before. And we've got these two new variables, alpha and beta, that represent how often these various types of decisions happen when we're interpreting the results of our experimental data. So the alpha and the beta represent the mistake types. And they're also kind of in order. So if you know the Greek alphabet, it's quite similar to the Roman alphabet that we use. So alpha is the first letter in the alphabet, and then beta is the second. Alpha, beta. So alpha represents the number of type 1 errors we're going to make, how many false alarms there are. And then beta represents how many misses, how many type 2 errors we're going to get in this decision-making process. And then the other halves of these equations are just 1 minus alpha and 1 minus beta. So you might notice that the alpha and the 1 minus alpha quantities reflect what's happening when the null hypothesis is true. So 1 minus alpha reflects the number of times that we actually get hits or correct acceptances, you could say, where we accept the null hypothesis when it's actually true. So these are right answers, so to speak. And then 1 minus beta are the other kind of right answers. So those are the correct rejections where, we don't have COVID and we decide that we don't have COVID, that sort of thing. But the difference between the two is in what decision we make. So when we accept the null hypothesis in this situation, we get 1 minus alpha. When we reject it, we get alpha. Together, if you add these two up, they're going to add up to 1, right? So let's say that 20% of the time you're making these false alarm mistakes. That means that 100 minus 20 equals 80% of the time you're getting correct acceptances or hits, right? These have to add up to 1, the entire proportion underneath the distribution that you're playing around with. That's why it's always 1 minus alpha relating to alpha, and then in the other sort of objective scenario, 1 minus beta is relating to beta on this side. So every time you're rejecting the null hypothesis, you're not accepting it, and vice versa, right? So there's two sides of the coin there. Although it's not so much a coin as it's just your decision-making process. So I don't know what the right analogy is for a physical object representing a decision, because when you flip a coin, randomness decides for you. We're not doing that. We're actually making a decision as sort of rational human beings, or human beings trying to be as rational as possible. But like I said before I don't figure out how to explain that correctly, I will remind you that alpha equals the acceptable rate of type 1 errors for a hypothesis test. And the acceptable rate that normally we use in statistics is 0.05, or 5% of the time. Basically, this comes from that guy, Ronald Fisher, who I haven't actually told you about. He's in the next section of this lecture. But he's a famous statistician from the early 20th century who kind of totally came up with this hypothesis testing paradigm, and is influential for that reason. He did a variety of other things as well in the world of stats. I'll tell you more about him next time. But he made the decision kind of for us that it's okay to make type 1 errors on about 1 out of every 20 hypothesis tests. So this is that kind of 95% number, again, that we've seen before, because 5% of the time we're going to be making mistakes when our null hypothesis is true. And then 95% of the time we're going to get the right answer, as it were. Yeah, like I said, though, this is conventional. It doesn't have to be the case that your alpha is set to 0.05. You can move it around if you want. Sometimes you see it set to like 0.01, or maybe I think in some cases people might set it to 0.1, or maybe even less than 0.01. I can talk about that in a second. But since conventionally alpha equals 0.05, if you increase alpha to like 0.1 or higher than that, that means you're going to be making more mistakes with the interpretation of your data than you would sort of conventionally. So you might raise a few eyebrows if you do that, because it's going to make it look like you're trying to get a significant effect out of your data, even in cases when you don't have one. So people might object if you tend to do that. And I'll say as well that this is sort of the criterion that is commonly used, like in linguistics or other social sciences. In the world of the physical sciences, they have a much stricter criterion, like in physics itself. And I don't know exactly what it is, but it's probably going to be set to be more like 0.001 or even less than that, right? Such that you're making very few mistakes. You have to have a lot of evidence against the null hypothesis in order to reject it in those cases. We're a little laxer in the world of linguistics, it turns out, because of Ronald Fisher. The beta variable represents the rate of type 2 errors for a hypothesis test. Yeah, and so that one's up here. That's where the null hypothesis is false. So something's going on, we just miss it. And then how often are we willing to make type 2 errors? And that kind of depends as well on how often we get these correct rejections, which is 1 minus beta. And that quantity is known as the power of a hypothesis test. And we'll talk about that more in the next couple of weeks. I have a whole specific lecture about that one that we can walk through. But this is an important concept here, because it's basically telling you how often, when something is going on in your data, will you actually find that something is going on in your data. This is kind of like the, pot of gold at the end of the rainbow here. Everybody wants to get like a significant effect out of their data so that they have something to report. That is kind of changing a bit in the world of social sciences as well, because of something called the replicability crisis, which I can't get into totally right now, but I will in the future. But people, when you run a study, when you put in all the work to design and like find the subjects and collect the data and analyze it and all that stuff, you want to have like a story at the end saying, oh, look, there's something going on here. So people often will ask, before they even take this class, and maybe this question has popped into your head as well, like, how many subjects do I need to run in my experiment? And what that depends on is this factor here, how much power there is in your statistical test. How likely are you when something is going on in the world? How likely are you to be able to identify that something is going on given your data? Not going to answer that now, but I will to the best of my ability in a future lecture. I will just point out that what that value is normally set to is 0.8. So basically what this means is that 80% of the time that something is going on in the world, you will identify it if you run the experiment sort of properly and interpret it properly as well. But what that means, since 1 minus beta and beta have to add up to 1, is that we'll accept type 2 errors on 0.2 of our hypothesis test, 0.2 of the whole proportion of the distribution, which means 20%. So basically, 5% of the time we'll make alpha mistakes, we'll make false alarm mistakes, and then 20% of the time we'll make miss mistakes. So 5% of the time we'll have false positives, 20% of the time we'll have false negatives. And this is the way it works in linguistics or social sciences. And again, one of the reasons why is we're just more likely to guard against making those type 1 errors because we tend to make those errors more often than the type 2 errors. So we're trying to work against our sort of innate bias as human beings to see patterns out in the world. And that, can feel a little bit counterintuitive, but it's just like forcing us to sort of reach a higher level of evidence before we actually say, yeah, something is going on. And like I said, before, we may have a stricter criterion level if we're doing like physics and we want to say, whatever random thing, I've discovered a tachyon, something that goes faster than the speed of light. Are you sure? Like, what is your p-value for that test or what have you? I can't get into all the details because I don't really know them all that well, but you'd have to have a really huge, clear batch of evidence to say, well, there's something like groundbreaking going on here, and that p-value would wind up being really, really small in whatever test you have to run. And you can also think about it in terms of, say, COVID testing, right? So when you go get a test for COVID, what's your bias there? Would you rather have the mistake where, you think you have the disease and you don't, or would you rather have the mistake where you do have the disease but you think you don't? And I think most people in that case would want to avoid the miss, right? If they have COVID and they go get tested for it, they'd want to know, right? They'd want to sort of maximize this quantity here, this 1 minus beta, and minimize beta for that reason. And if you get a few false alarms along the way, maybe that's not so bad because you just have to quarantine for 14 days as opposed to, possibly winding up in the hospital without, or sending other people to the hospital, of course, because you spread the disease without knowing it or something like that, right? So this can vary, right? So we can decide which sort of mistake to make more often, depending on sort of the endeavor we're involved in. But in either case, we're never going to be perfect is kind of the main takeaway from this. So when we do linguistics, normally, like formal linguistics, like in phonology or syntax, and we're trying to describe some pattern we see in a language of the world that we're interested in, normally you want to get it totally right. Yeah, you want to find out what is the rule involved in the generation of this sentence or phonological pattern, or what are the constraints, even for that reason. And this is the way I was trained back in the days. Like if your story isn't perfectly right, then you haven't sort of gotten specific enough about what the pattern is, and you got to kind of go back to the drawing board and get it down so that you can explain exactly what's going on. That's sort of the generative way to do it, because then your rules will be able to generate all the different forms of the language. It's a little bit different in stats, because in stats we just assume underlyingly that everything has variability and the boundaries are fuzzy, so things will get a little messy. So we're always going to wind up with a few mistakes, and we're making just our best educated guesses in spite of those mistakes, or in spite of the variability that we kind of have to try to see the patterns through. So I'm just repeating this again. And I'm also going to make another point here. On top of the fact that we're always going to make mistakes, we can't sort of change these values independently of each other. So the values of how many mistakes we're going to make. I'll try to walk through this a little bit more slowly, even though I'm talking kind of fast here. But these two rows here, the accept the null hypothesis and the reject the null hypothesis, reflect the two kinds of decisions we make, right? So we're either accepting or rejecting whatever we originally thought about the situation. And those reflect these two types of mistakes that we can produce here. And you might want to look at this and say, well, wouldn't it be great if, rather than like 5% of false alarms and 20% of misses, why don't we crank them both down to 0 or as close as we can get to them, right? So like, why don't we do like 1% misses or like, and in conjunction with like 2% false alarms? Wouldn't that be way better than like 5% and 20% because there's far fewer mistakes, right? Or even crank them both down to 0 if we could, right? You can't do that. They're related to one another, right? So if you think about it, let's say we look at this row of rejecting the null hypothesis. If we want to reject the null hypothesis more often, we're increasing our alpha level. So that's the case like where I said conventionally it's set to 0.05, but you could increase it to like 0.1. And you might do that if, say, you want to increase the power of your test, right? If you want to make sure that you know that you have COVID when you do have COVID, that's what you have to do, is sort of just guess that you do more often. And in so doing, you're going to make more false alarms. You're going to get more false positives as a result of your experimental process. And then when you increase power, you're going to have to decrease your misses, right? So increasing the number of these errors, the alpha errors will increase, increasing the number of alpha errors you make will decrease the number of beta errors you make. And vice versa. If you go the other way and say, I'm going to accept the null hypothesis more, I'm going to increase this beta error, that's going to decrease alpha. There's a trading relationship there. You can't get them both to go down or both to go up, what have you. If you make more of one, you're going to make less of the other, and so on and so forth. Just remember, we're making decisions here. And what we can't control in this process, the thing that makes it impossible for us to be perfect is that we can't actually know the underlying reality perfectly. And we can't control what that underlying reality is either, right? The null hypothesis is either true or it's false, and we're just making our best guesses as to what it actually is. And so we control this part of the equation, but not this. And in shifting more from one side to the other here, we either get more of these mistakes or we get more of those mistakes, but we can't drive them both down to 0. Okay, so a little frustrating. I'm sorry, but I think I've said this before. Life isn't perfect, and neither am I. So we just go on trying to do the best we can. Okay, so a lot of preamble to the answer to our question. Our example hypothesis test yielded a p-value of only 0.002. What does that mean for our hypothesis? That means that 0.002 of the hypothesized sampling distribution is to the left of our sample mean. That's a small amount of the whole thing. And I'm drawing up here again to kind of give you the graphical interpretation of it. And like I said before, by convention, we set alpha to equal 0.05. So again, normally I draw this on the board. I'm having to jury rig something here graphically, maybe for the best because my drawing skills are as bad as my writing skills. And what you have here is this alpha criterion, and I've shown it to you with respect to the entire sampling distribution, roughly where it should be, such that there's 5% of this distribution to the left of this alpha criterion. Remember, we were testing, the less than hypothesis in this particular case. It turns out mathematically, you have the skills. I've taught you what you need to know to figure out exactly where this alpha criterion should be, i.e. what value of VOT you'd have to have a sample mean less than to give you sort of this significant result, or to tell you like what value of VOT you'd need to have such that 5% of the distribution is to the left of it, kind of saying the same thing twice. I'm not going to walk you through the math here, but you might as well think about that. You should be able to know exactly where this alpha criterion is. For our purposes right now, all we care about is sort of this relationship between the percentage or proportion of the distribution to the left of this sample mean and how that compares to this 0.05 criterion we've set effectively arbitrarily to sort of interpret the results of our test. And basically, the important relationship is that since 0.002 is less than 0.05, we're going to reject our null hypothesis in this case. We're going to accept the alternative hypothesis and say something is going on. Our default expectations were that VOT was 100 milliseconds. We just kind of picked that out of the air, but that's what we're kind of starting from. And we find, based on our experimental data, that that is not the case. We're rejecting that null hypothesis, and we're going to say that instead, the VOT has to be less than that value. Again, we don't find out if we're right exactly, and we don't find out exactly what the value of VOT is, the mean value of VOT is in the population world. We just say this hypothesis is wrong. Based on our best guess, based on our best data, this hypothesis is not correct. We're going to reject it. That VOT has to be something less than that value. That's the result of our test, basically. I'm going to remind you here that decision could be wrong, right? That's what I was talking about with respect to like the false alarms and the misses. Our decision is not always going to be right, and sometimes, in fact, it will be wrong if we play the game according to the rules that Ronald Fisher wrote up. So it's possible that we can get a sample mean of 94 milliseconds, even if the true population mean is 100 milliseconds. And in this case, rejecting the null hypothesis will give us a false alarm, because the underlying reality is that nothing is going on, and yet we think that something is going on. We've rejected that nothing hypothesis. Just to kind of put this out there in graphical form again, if you run this experiment like thousands and thousands, millions of times, you're going to get sample means along this distribution, right? That's the sampling distribution. And then sometimes those sample means will be out here in the tail, such that they are lower than the value specified by this alpha criterion. That's going to happen 5% of the time. If you run this experiment 100 times, 5 times you will make false alarms on average. 5 times you will have sample means out here in the tail, such that you reject the null hypothesis, even though you shouldn't. But remember, we don't ever really find out what the true answer is. We don't ever find out that we're wrong when we're wrong. We just make this decision based on the rules of the game and go from there, because we know we're never going to be perfect. And we just say we're going to accept the fact that we'll be wrong 5% of the time in this game, the linguistics version of the game. So we're drawing a reasonable conclusion about the underlying reality based on the data we get from our sample. That is the null hypothesis significance testing paradigm in a nutshell. And I guess since I haven't talked about this explicitly, I will go back to this term significant and say, oh, in this particular case, we got a significant result. And what that means is the data is telling us something. The data is telling us that our null hypothesis is wrong. It's signifying the fact that there's something going on in the data that we did not expect. So I think that's all I want to say for now about all this. In the next video or part of this lecture, I'm going to talk about t-tests. But this is kind of the core of what we're doing. So you should understand null hypothesis significance testing by now. But if you didn't understand it the first time through, feel free to go through the lecture again, because it's not easy to wrap your head around, and it's also very important. So you got to understand it in order to understand basically the whole rest of the class. But I'm going to stop now. I will talk about t-tests in the next video and how they differ a bit from this sort of z-test approach that we use for this first example. All right, I'm going to stop talking now because I've talked too much already.